Hello. In this video, I want to try to answer the question, what do we mean, what does it mean for two graphs to be really the same? Okay, so let's look at these two graphs that I've drawn here. So they look pretty different, right? The drawings are different. If you said to like a kid, are these two things the same? They'd say no, right? They look different. But remember, a graph is really a finite set, the vertices, and something that tells us which vertices are connected, right? So a set of vertices and a set of edges. And when I look at this a little closer, thinking about some of our graph theory terminology, I can see, well, they actually have a lot in common, right? This graph on the left has 6 vertices, and this graph has 6 vertices. When I look at the degree of every vertex in this graph, I get degree 3, degree 3, degree 3. All the vertices have degree 3. And actually, the same is true for the other graph. All of the vertices have degree 3. If I count up the number of edges in the first graph, I get 9. If I count up the number of edges in the second graph, I get 9. So actually, when I start to think about this a little more deeply, I think, well, maybe actually they have a lot of similarities. Maybe are they sort of the same? And what would we even mean by that? And so what I want to do today is give a rigorous definition of what it should mean for two graphs to be the same. And when they're the same, what we say in mathematics is that they're isomorphic. So I want to share now my iPad with you all. And let's see, here it is. Okay, so this is the definition of graph isomorphism. If I have two graphs, a graph G that has vertex set V and edge set E, and a graph G prime that has vertex set V prime and edge set E prime, we're going to say the graphs are isomorphic, or that G is isomorphic to G prime, if there exists a bijection, phi, on the vertex sets. So what's a bijection again? Remember, this is, maybe I'll write it in red. This is a function that is both injective and surjective. So both one-to-one and onto, such that UV is an edge in the first graph, if and only if, how did that phi disappear? Phi of U, phi of V is an edge in the second graph. So let's look at some little examples, and then we'll go back to the one we started with, okay? So for example, let's suppose that G is the graph that looks like A, B, C, and G prime is the graph that looks like U, V, W. Are these two graphs isomorphic? Well, we can define a function from the vertex set of G to the vertex set of G prime, so U, V, W. So we'll define phi by, I have to tell you what phi of A, phi of B, and phi of C are. So phi of A is going to be U, phi of B is going to be V, and phi of W is phi of C is going to be W, okay? So we can see that this is a bijection, right? A goes to B, A goes to U, B goes to V, and C goes to W. So it's a bijection. And for these small examples, we won't write out that it's a bijection. Like we'll just sort of observe that it's a bijection, right? Because we can see it. There's no formula really to check. And then let's check the other thing though. So what are the edges in E? So there are two edges we have an edge AB, and so this is in E, and if I look at phi of A, phi of B, well, phi of A is U by my definition, and phi of B is V, and I can see, in fact, UV is one of the edges that I've drawn in G prime, okay? The other edge in G is the edge BC, and what I see is that phi of B, phi of C is going to be, phi of B is V and phi of C is W, and that actually is the other edge in G prime. And so what I can see is that I have a bijection on the vertices, and two vertices are connected in G if and only if their images are connected in G prime, okay? So these two graphs are isomorphic. The isomorphism doesn't have to be unique. So here's another isomorphism between the two graphs. So I'm going to call this one psi, and psi goes from the vertex set of the first graph to the vertex set of the second graph. This time, though, I'm going to say phi of A is equal to W. Oops, sorry, that's psi. Psi of A equals W. Psi of B equals V. And psi of C equals A. So I claim this is an isomorphism too. Why? Well, again, I have to look at my two edges in E. So the edge AB is in E, and what's phi of A, phi of B? Well, phi of A is W and phi of B is V, and there is the edge, like VW is the same thing as WV, right? It's in that graph. So this is still an edge in, G prime, or E prime, right? Because the edges are unordered sets of vertices. Moreover, if I look at the edge BC in E, and then I look at phi of B, phi of C, then what phi of B is V, phi of C is U, and UV or VU is an edge in E prime. So these two graphs are isomorphic in two different ways. I can match up A and U, B and V, and C and W, or I could match the vertices in the opposite order and match A with W, B with V, and C with U, okay? And those are the only two isomorphisms that work between these two graphs. The B and V have to go together because one of the things that isomorphisms preserve is the degree of a vertex, right? And that makes sense because the degree of a vertex is the number of edges incident to that vertex. And what I know is that because I have an edge in one graph, if and only if the image of those vertices are connected in the other graph, that that maintains the degrees, right? Each vertex, the vertex here has to be paired with the same number of vertices, has to have the same number of edges as its image in the second graph under an isomorphism. Another way of thinking of isomorphisms is two graphs are isomorphic if one is really a redrawing or a relabeling of the other one. So in this case, you know, I have my original graph ABC. I drew it in a straight line, but I could also just sort of bend bend the A and C down, and then I'd get something that looks just like my second graph. Okay, so let's go back to, or before we go back to the example that we started with, I just want to list off some things that are preserved. So graph isomorphism preserves what? Preserves degree sequences, right? Degrees of vertices. So if my degree sequence in one graph is this, I have to be able to order the vertices in the other graph so I get the same degree sequence. It preserves the number of edges. So two isomorphic graphs have to have the same number of edges. Of course, they have to have the same number of vertices as well. Number of vertices. And as we learn more graph terminology, we'll be able to see other things that graph isomorphism preserves as well. Okay, so let's end by going back to this example that we started with, okay, and ask, are these two graphs isomorphic? Certainly they have the same number of vertices, the same number of edges, and the same degree sequences, so 3, 3, 3, 3, 3, 3, 3. But are they really the same? Is there a way of relabeling, say, this graph, or redrawing it so it looks like the other one? Well, let's see. Let's keep the L and the H here. I'm going to take this K and I'm going to move it down here. And I'm going to take G, whoa, and move it up there. And now already you can see, after I pull those vertices, that yeah, those are real. It was really two ways of drawing the same graph. We can undo this. Look at that. Whoa. So if you have a program like this, it allows you to sort of tug at vertices and maintain the connections between them. And then you can just see, yeah, there are lots of ways of drawing the same thing. And then that these two graphs are isomorphic, where by redrawing them, I can see how to get the isomorphism, right? I could define a function phi from A, B, C, D, E, F to G, H, K, L, M, N, where I could say, let's A go to L, and B go to H, C go to G, D go to K, and E go to N, and F goes to M. So my redrawing tells me what the isomorphism should be. Okay, so you'll have lots of opportunities to look at examples in worksheets and the homework. Thanks a lot.